And welcome back. Today we are going to be going over chapter 5 in the notes, and we're going to be looking at the using area, slope, or velocity graphs to quantitatively make position and acceleration graphs shape. So basically what we're going to be doing is we're going in the opposite direction from what we have been going in. So before we have been going from position graph to a velocity graph by graphing the slope of the tangent lines, or by graphing the slopes. Now we're going to go the other way. We're going to go from velocity to position graph, and you'll see that by doing this, we'll have to be, rather than taking the slopes, we'll be doing the inverse, which will actually be taking the area under the line. So let's start off with this fill in the blank that we have here. So area of a rectangle is the product of length and width, and a triangle is just half the rectangle's area. On a velocity graph, the area between the x and the graph for some time interval represents the position change. So what's another name for position change? It would be the displacement. So this is displacement here of the object in that time interval. This is true because the area unit would have to be a meter, because the product, if you think about it, if you have a velocity graph, you have velocity on the y-axis, you have seconds on the x-axis. The product of those two, seconds cancel out, and you end up with meter. So the area under the line corresponds to the displacement of the object. So the position of the object at the end of the time interval can be found by adding the initial position or position at the beginning of the time interval to the displacement. Okay, so final position is equal to your initial position plus your displacement. That should make sense. This is just this displacement equation rearranged, solving for final position here. Okay, so basically what happens is you find a displacement by finding the area under the curve, and then you add that to your previous position, and that will give you your final position of where you're currently at. So to summarize, a position graph can be made from the area under the velocity graph. 2. The slope of a velocity graph must be the acceleration as reviewed earlier. So this is what we've been talking about previously in the last week actually. So the amount of the acceleration is found by calculating the slope of the velocity graph. Since the velocity graphs we have seen are made of line segments and no curves, and since the slope of each line segment is constant, that means that the acceleration graphs of the series must be horizontal. What this is saying is that horizontal is that when our velocity graphs are straight, like lines like this, is linear, the slopes of these, right, which would be the acceleration graph, would be horizontal lines joining together. And we said before, we'll join them together with open circles. Don't worry about this. Just draw them open circles. So let's go ahead and start with the problem on the next page. Okay, so this is the top of the next page. I just zoomed in on the top two squares there. So we have a velocity graph here on the top left. Okay, on the right here we have the position graph here. So we're used to going from position to velocity, right? To go from position to velocity, we use the slopes. Okay. We need to realize now that we're going from velocity to position. So to go from velocity to position, we're going to graph the areas. Okay, so you need to know the difference here of which way we're going. We go from velocity to position, we graph the areas. And the areas are going to be equal to the displacements. Okay, so remember that. It's not your position, it's your displacement. It's not written on here, but we need to have a starting position. Okay, let's just say our starting position, we'll say, is -4 meters. Okay, this will always be given to you. It's just not given to you on this problem because we forgot to write it in. So our position at 0 seconds is -4. If you look at here, each unit here would be 2 meters. So -4. So what I want you to do is plot the position and then write in the coordinates. So we have times 0. The position of -4. Okay, so for each second that occurs, so from 0 to 1 second, to find your position at 1 second, then you find the area under this velocity curve. Okay. When I say under the curve, I'm meaning you find the area from the line, from where it's currently at, to the x-axis. So I know this is over it, but I just call it under it because that's the term that you use. So we're going to find this area right here. I'll try to highlight it here. From 0 to 1 seconds, it'll be this area right here. Okay, this area right in here is the area we're going to have to find. To do this, what we'll do is we'll split this up into triangles and rectangles, and this will make it very easy for us to find the areas. Okay, so looking at this area right here, I can split this top part into a rectangle, so this rectangle right here, and then we have a triangle right here. And then we just add them up and find a total displacement. So here we go. So the height of this rectangle is 2, 4, 6, 8 meters high by 1 meter across, which makes a total of -8 meters. Okay, I should put negative here. This is totally this is -8 meters. This triangle here is 2, 4, 6, 8 by 1. We know triangle is the area of a triangle is 1/2 base times height. So base times height would be 8 times 1/2 would be 4, -4 here. So I take these two values and add them together. -8 plus -4 would give me a total of -12. I'll circle this here so it pops out at me for my displacement from 0 to 1. So what does this mean? This means from 0 to 1 I displace a -12 meters, which means for my current position I will at -4 I'll subtract 12 from that, which will leave me with the position of, well, -4 minus 12 would be -16. So at, if you want to see the math here, we're at -4. I'm going to add my displacement of -12. This will give me a final position of -16. So at 1 second, I'm at -16. So 2, 4, 6. -16 is here. So it'd be at 1 second is -16. See how that works? And we just go through and do this for every second in time. So let's go ahead and do this again. Here I just see one triangle here. This triangle is 2, 4, 6, 8. 8 tall with 1 width. Oops. With 1 width. Let me move this up a little bit. 8 times 1 is 8 divided by 2, because it's a triangle, it'll give me a -4 for that one. So remember, my position is not -4, my displacement is -4, which means from this position right here, at -16, I still have to move backwards 4 more meters. So at 3 seconds, I move backwards 4, so 2, 4. Again, I'm plotting the areas, and the areas correspond to the displacement. So this would be 2, -16 minus 4 would be -20 for that one. Okay, so you can start to see the curve developing here. So we're going from a straight line to actually a curve. Let's do the next thing. Next, I'm going over the x-axis, so now I'm going in the positive range. You can see a triangle right here. See that triangle there? So I have a 1 for a width, so that's easy because I'm going over by 1 second each time. And I'm going up to 4. Okay, so 4 times 1, base times height is 4, divided by 2 would be a sum total of +2 on that one. I'm just go through and do all these right away, get these done with, and then I can go ahead and plug these in for my displacement. So you can do it either way. The next one, it's 4 high by 1. Okay, and same as here, 2, 4 by 1. So I will have, this will have an area of 2. This will have an area of 4 for a total area of 6, which means the displacement will be 6 right there. Look at this one, we got a nice big rectangle here, 2, 4, 6, 8 by 1. Give me a total area of 8. Same with the next one, looks like it's the same, 8. I have a height of 8 here for this triangle with a width of 1. Which give me a total area of 4. I'm just going quickly over this. I'm just kind of doing this in my head, the 1/2 base times height. And now I have a, don't get confused now, I have a triangle right here. Remember, we go to the x-axis. This is the triangle right there. You can see that triangle there. So this is about 1, and the height goes from 0 to 2, 4, 6 to a negative 6 here, which gives me a total area of minus 3. So these circled, what I circled there are the displacements. So we go ahead of here. I'm already did 2 seconds. So from 2 to 3, I have a total displacement of plus 2. So at 3 seconds then, plus 2 would give me right there. At 3 seconds, I'd be at negative 18. Next one, I'm going a little quick here. So ask questions if you have questions, or you can add comments on here too. I'll take a look at the comments if you have questions. From 3 to 4 seconds, I have a displacement of plus 6. So negative 18 plus 6 would give me a position of negative 12 on that one. So at 4, I'll be at negative 12 at 4 seconds. 4, negative 12. Make sure you got these coordinates in so I can see that you're doing the math right. From 5 to 6, I have a displacement of 8 again. So negative 12 plus 8 will give, remember, 8 is my displacement. My current position is negative 12. Okay, so negative 12 plus 8 will give me negative 4 for a position there at 5 seconds. 1, 2, 5, oops, negative 4. Now I'm going from 5 to 6 seconds. What's my displacement? Sorry here, I moved this over a little bit. So from 5 to 6 seconds, what's my displacement? It's 8. So from 5 to 6 seconds, that means I move a positive 8. So negative 4, I'm just showing math here, plus 8 will give me a plus 4 for my position. So 2, 4, this will give me a 6 and a 4 here. Now remember, this is going down, but I still have a positive area. My next area is right here. So that's positive, so I still have a positive 4. So from 6 to 7 seconds, 6 to 7, I have a positive 4 for my area. Okay, so I still move up, so I'm at 6. Hold on here in a second, let me take a look. Sorry about that, my key was actually wrong. So 2, 4, 6, 8. Divided by 2 give me a displacement of 4. I'm already at 4 meters, so I need to move up from 6 to 7. I need to move up 4 more meters, which would leave me at position of positive 8. From 7 to 8, I move down 3 meters, or I should say the left, or I displace a negative 3 meters. So I'm actually going to be in between here. So 8 minus 3, I'm sorry, yeah, 8 minus 3 would give me a position of 5. So 2, 4, and then 5 will be right in the middle here. 8 seconds, I'll be at a position of 5. Okay, so you can kind of see the curve that we have here. So this is how this works. So now we just take your pencil, and we'll see if I can do this without messing up. It's going to be kind of tough here with a computer, but we'll see what I can do. You just try to connect the dots with a nice curvy line here. Nice parabola, and like that. So you get the idea. I'm trying to connect the dots here, so even goes up a little bit more here. Okay, so that's how we go from velocity to position. Remember, we take the areas under the curves. You can't, if you have trouble seeing the areas, maybe shade them in. Here, here's what the areas will look like, and that's how you go from velocity to acceleration. Watch the next video here. I'll show you. I'll quickly go over how we get from velocity to. I'm sorry. This one you go from velocity to position. Next video I'll show how to go from velocity to acceleration, which you already know, and let's use that as review.